In today's video, we are going to look at PES graphs and just learn how to read them and try to figure out what information we can get out of these graphs. So let's look at a PES graph, which stands for photoelectron spectroscopy. And what this graph is going to be able to tell me is a couple things about the atomic structure of an atom. So specifically, what this will tell me is the electron configuration. And so we'll figure out what the electron configuration is from the graph. And once I know the electron configuration, that will also help me identify what atom I'm looking at. So let's try to determine these two pieces of information from this PES graph below. So on this graph, I have a relative number of electrons on the y-axis, and then on the x-axis, I have binding energy. So what I can see over here is that on the left, this represents a higher binding energy. And if my binding energy is higher, what that means is these electrons are very tightly bound to the nucleus, which means they're very close to the nucleus. Now, in this case, it would just be this first peak on the graph would just represent my first orbital or my first energy level. And if you guys remember from quantum configuration, this would represent my 1s orbital. And in terms of how many electrons are in there, well, each interval here represents one electron. So this is a fully maximized 1s shell. So we're going to say that this first peak represents 1s2. Okay, now as we get a little bit further down, so if we look towards the right side of our x-axis, we can see that the binding energy decreases. And if my binding energy decreases, that means that these electrons, they still have a nuclear force of attraction, but they're not as much attracted to the nucleus. So we're getting farther away from the nucleus as we look at these next two peaks. Okay, we're still fairly close because my next peak over represents my next energy level, which is 2s. So this next peak here is 2s2, okay? And how do I know that? Well, you guys remember from, I won't go through the whole thing per se right now, but this quantum filling pattern, we call it Aufbau. And what Aufbau means is that electrons fill the lowest energy levels first. Now, the lowest energy levels is also represented by the highest binding energy. So like, for example, 1s will fill first, and then when that's full, it goes to 2s, the electrons will go into 2s, and when 2s is full, the electrons go into 2p, and then 3s, and so on and so on. And we use these arrows to show the direction of electron filling. So for example, 1s2, 2s2, because 2s is full, I'm going to go to 2p, and so that's represented by my next peak here. This would be 2p3. So remember that each interval here represents one electron, and I know that because, again, the 1s2 is full, the 2s2 is full, so the 2p3, the p shell is not full in this case, it's half full. So my electron configuration overall for this graph is 1s2, 2s2, 2p3. That's a total of 7 total electrons, which means the identity of my atom here is nitrogen. Okay, so nitrogen has 7 total electrons in its ground state. Okay, let's try another question now, a sample question from one of the older AP free response exams. And so similar kind of thing, okay? Let's use this graph to determine the electron configuration and the atom, the identity of the atom. Let's try to figure out both of those things based on this graph. So very similar. If I look at the x-axis, the higher binding energies are on the left. So again, this represents my first orbital, or 1s. And as you go this way on your x-axis, you're getting farther and farther away from the nucleus. Okay, so each peak represents your next energy level. So for example, the very first one, this is 1s2. So then this part represents energy level 2, or n equals 2. This part is n equals 3, and then over here is n equals 4. Okay, we're getting farther and farther away from the nucleus. And in terms of the relative electrons, just be careful on this one. If we look at the interval, like for example, this line that I'm highlighting, that's 2 electrons. And then this line up here, this would be 4. Okay, so just the scale is different on this graph. And then this up here would be 6. So for instance, if I go to my next orbital or my next energy level, n equals 2. This first peak is 2s2, and then this would be 2p6. And then if we scroll over, this would be 3s2. This higher one is 3p6, and then the final one is 4s2. So if you put all that together, my electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And if you count all of that up, that will give you 20 electrons total, and that correlates or matches the atom calcium. Okay, calcium, the atom. And I should specify, yeah, we're looking at the atom here, not the ion or anything like that. This is the atomic configuration or the electron configuration for the atom. And the question probably would specify if we're looking at an ion versus an atom. And let's do one more. So here's another variation of a PES graph question. So I'm shown here silicon, but it's a partial PES graph. And there is a peak missing. So we're going to fill that in first. But before we do that, if I look at my periodic table, I can see that silicon is over here, atomic number 14. So let's write down the electron configuration of silicon first so I know what I'm looking for, okay? So silicon, again, 14 electrons is going to be 1s2, 2s2, 2p6. So that's 10 electrons, right? 6, 7, 8, 9, 10. So keep going, 3s2. And then 3p2. So this is the configuration that will give me 14 electrons in silicon. So if I use my PES graph, what I can see again, binding energy, higher energies are on the left and lower energies are on the right. And so this first peak that I'm looking at, this is 1s2, and then this will be 2s2, 2p6, 3s2. And so I'm missing a 3p2 that is not shown on my PES graph. So I'm going to show that by putting a peak here, and this would represent 3p2. And on this graph, the relative electrons, each interval, each line represents 1 electron. Okay, so you just have to look at your graph carefully in these questions because sometimes the axis does change. Okay, and there is a follow-up question. It says here, using atomic structure, explain why the first ionization energy of Ge is lower than Si. Okay, so first of all, we have to remember what is ionization energy. It's the amount of energy needed to remove an electron. Okay, so energy needed to remove an electron from an atom. And so it makes sense that Ge, if we look at our periodic table, Ge is underneath silicon. So Ge has a greater radius. And also you could write down the full electron configuration for Ge. There's 32 electrons. So you can tell that Ge has an extra orbital. So it'll go into the like the 4th energy level. And so because the radius is bigger of Ge, we can say that the attraction of the valence electrons to the nucleus is less. So let's make a note, okay? Yeah, because of the atomic trends, those can be difficult to explain. So the first ionization energy for Ge will be lower because Ge is a larger atom. And so because it's a larger atom, its valence electrons are farther away from the nucleus. Because they're farther away, those valence electrons, or that one valence electron, the first ionization energy, that one electron we're going to focus on, it will not have a very strong attraction to the nucleus. So in other words, it will have a very low binding energy, which makes it easier to remove. So the valence electrons are farther away from the nucleus, giving them less binding energy, making it easier to remove. Okay, and you can word that a little better and look at the answer key on the College Board website to get the wording a little nicer, but hopefully that gives you the idea. And I hope this quick review lesson will help you review how to read a PES graph and to determine different parts of atomic structure that you can determine by looking at this graph. Thank you for watching the video and have a great day.